Okay, class. So let's recall back. Can you see the slides?
Yes.
Can. Good. Thanks. Okay, so where is it? Okay, so let's recall back what we did last class. So we just discussed about magnetic field, very important field, a lot of uses for human. We talk about what is meant by magnetic field, a region where a moving charge experience force. We talk about what is the formula to find the force. F equals to BIL sine theta. Then from here we define B. B is force per unit current per unit length. Okay, placed perpendicular to the field. Yes, these two we worked out yesterday. Introduction. Okay, so we done this. Remember the three pattern of the magnetic field pattern, mainly solenoid, and three ways how to strengthen the solenoid magnetic field. How did you strengthen the solenoid magnetic field? Use more current, more number of turns per unit length, place a soft iron inside. So BIL sine theta. Okay, only magnetic field strength got another name called magnetic flux density. Magnetic flux density, magnetic field strength is the same name. Same meant to be the same quantity. Okay, I told you the unit for magnetic field strength, Newton per ammeter per ampere per meter, but we may call it as Tesla. So every region has a different Tesla. Tesla is a very big unit, as I told you. MRI, one of the strongest, 3 Tesla we can found on the surface of the Earth. Okay, Earth magnetic field is quite big, 50 microtesla. Okay, so we done these questions. Okay, today's lesson, we're going to work out how do you get to measure magnetic field strength. Okay, now you are sitting in front of the laptop, you are in a room. Imagine, so remember, there is a magnetic field experienced by you. The magnetic field in your room is horizontal, right? It's horizontal because this is the Earth. We are at the equator. So of course the magnetic field is horizontal, or else it's going to be horizontal. It's horizontal. So you want to know, measure how much is the Earth magnetic field. What device do you use? Okay, that's what we're going to discuss today. Right. Let's get this first. Yeah. So measuring of magnetic flux density. How do you measure magnetic flux density or magnetic field strength? We use one device called current balance. It's a current balance. Okay. It's a little complicated. The current balance is actually, you see this picture up here. It has a pivot at X and Y. X and Y is a pivot. The left hand side is actually an insulator made of a plastic or maybe an insulator. And the right hand side is a rectangular wire, like a rectangle wire shape, stiff one, so it's straight. Okay, and we have a circuit at the bottom. So what we do, I tell you, just look at the picture. I tell you, First, we let the current flow. Current, you see that there is a battery here, accumulator. The current flow. The current will flow past the X, and it will go to the wire and reach the Y and go down to the circuit back. So what happened? The current is flowing in the wire, no current flow in the insulator. So when the current is flowing in the wire, we place this movable wire A to B, the A to B section, to the magnetic field you want to measure. Okay, you want to measure Earth magnetic field? Make sure you put the line of AB is perpendicular to the Earth magnetic field. This is the biggest problem we're going to face now, because we don't know which direction the magnetic field is acting. Okay, you can use a compass maybe. Okay, so north south. So north south direction, the AB must be east west direction. You must place it, must be perpendicular. Then what do you do? Now you see the picture here. The current is flowing from A to B. The magnetic field is let's say left to right. Which direction the force will be acted on the wire? So use Fleming left-hand rule. The force found to be downwards. Use your Fleming left-hand rule now. The current is going A to B, FBI. Your middle finger is to A to B. Force is B is to the right. Okay, turn your index finger to the right. You see your thumb pointing downwards. The force is downwards. Okay, when the magnetic force acting downwards, what happened? The X and Y is like a pivot. Like a pivot. It's a movable rectangular shape. So when the AB force downwards, so the AB will pull down. What happened? The insulator will start to move up. Then what we'll do? We put some mass called rider. Some masses. We already have certain mass here, weight. We put some rider here. The total mass, some mass is hanging here. Until what happened? This weight counter-react to this moment, and the moment by the magnetic force. So the moment by the magnetic force, when it's balanced, the moment caused by the magnetic force must be same as moment caused by this weight about the pivot. Where is your pivot? X to Y is a pivot. So from there, we calculate the magnetic field strength. How do you calculate magnetic field strength? The moment caused by what? The moment caused by the magnet should be equal to the moment caused by the weight, mg. Moment, recall back your AS knowledge. Moment is what? Force times perpendicular distance, right? From the pivot.
Yeah.
In this case, the moment of the magnetic field strength is what? The force of the magnetic field strength, which is we know is BIL times with the perpendicular distance. In this case, where's the perpendicular distance? The X to B. Sorry, the Y to B. Or can say X to A. This is your perpendicular distance. So X times A is a perpendicular distance. Should be equal to mg times which distance? Distance between C to Y. Distance between C to Y. Yeah. So we use this concept, we work out the B. I we calculate from the, we put an ammeter here or millimeter, we can calculate the I. L, which L do you use? Anyone, which L do you use here? Length of the conductor. Where's the length of the conductor? The AB. AB is the length of the conductor, AB. So XA, so you can work out the B. This is a concept used by current balance to calculate what? To calculate the magnetic field strength of any magnetic field strength. But the only problem is you must make sure the AB line perpendicular to the magnetic field strength. That's quite tedious. So you have to use this compass at the side, maybe check where's the north-south direction. North-south direction is horizontal, north-south. Then you put the AB across like this, perpendicular. Why I say it must be a perpendicular? Because you see in the force of magnetic force BIL is supposed to be BIL sine theta. We never write sine theta because we assume sine theta is sine 90. Then remove it. That's why. Okay, so that's the description, yeah, the one I told you. XABY is a conductor, XDCY is an insulator. Both sections are merged, pivoted at XY, form a rectangular frame ABCD. Initially, riders are placed in CD to balance the frame horizontally. AB is placed current carrying solenoid, which provides a horizontal magnetic field. Cut AB perpendicularly, important, and downward. Okay. So this is the idea I told you just now. They use a moment technique. Weight times D2 equals to magnetic force times D2, sorry. Weight times D1 equals to magnetic force times D2. Magnetic force, we just put BIL because we make sure the magnetic field strength is perpendicular to the current. Okay. So any questions from here? So what do you use to calculate to measure the magnetic field strength? So you want to calculate the magnetic field strength in your room. So you need to have this device. After this coil goes down, you have to add some mass here until you balance it. Should not have air resistance. So it's quite tedious. Quite tedious. But not we have another device which can measure the electric field strength, magnetic field strength very, very easily and quite reasonable accuracy. Anyone knows another device which can measure magnetic field strength? Start with H. I don't think so. You come across with this. Hall probe. So Hall probe is another device. Is to measure magnetic field strength. Okay, the one in our physics lab. If you have a chance, okay, I think 18 February. Remind me. I show you the Hall probe. Okay, Hall probe is just a device, just like this. Okay, this. And you have connected to a millivolt meter. So this surface should be exposed to a magnetic field perpendicular. I think this length is about maybe 1 centimeter. The vertical height will be like maybe 20 centimeter of height to hold it. Okay, it's called Hall probe. We will do in depth about this later. Okay, but still in your in your syllabus, they want Cambridge want to understand the current balance. Okay, although it's like a primitive way of finding the magnetic field strength, but still Cambridge never removed this part. They still want you to understand what the current balance. Okay, more sophisticated one I think should be Hall probe. That also will be learning later. Okay, any questions, guys, so far? No questions? Okay, good. One example. Okay, so look at this question. It's about current balance. 1 minute for you. Read the question, look the diagram, try to figure out how you're going to go the question. Okay. So hope all of you have went through the questions. Hope you have the ideas in your mind how to handle it. Okay, so this is the diagram all about with the dimensions. Mass hanging was 20 gram. The AP was 15 centimeter, and QC also QC was PD is 18 centimeter. So first, indicate the direction of the magnetic force acting on the CD. So CD, which direction the force acting, the magnetic force? So current is to this direction towards the left current. Magnetic field is towards inside B. So use your Fleming left hand rule. Your force must be where? FBI. If you put it correctly, the force definitely downwards. The force is downwards. The first answer, force is downwards. Use Fleming left hand rule. Because use Fleming left hand rule about 2 years, right? Okay. Okay, calculate. Okay, calculate the magnitude of the magnetic flux density. So how do you do that? Anyone? So moment, right? The weight of 20 gram times what? 15 centimeter. The moment caused by the weight must be equals to the force of the magnetic field strength times the length. What is the length? What is the perpendicular length? 18 centimeter, right? The force you write in terms of what? Force you write in terms of what? BIL. We are looking for the B. I, how much? I given? I given or not? What is the current? Current is 2.5. So current given. L. L. Look at the diagram. Tell me, L use how much? Anybody? L use how much? Check from the diagram. L should be 10 centimeter, right? Should be 10 centimeter. Why 10 centimeter? Because the length in the magnetic field strength is to be used. Okay, not the entire CD length, the length in the magnetic field strength. Many times I stress you this. Okay, so that's the working. So this is the diagram. Take moment. So mg times 0.15 should be equals to f times 0.18. So f we put BIL, and the length is just the length of the 10 centimeter. So mg times 0.15 divided by 2.5 current, the length. Okay, 0.1. BIL. BIL. Okay, 0.18 is what? Times 0.18. Oh, the perpendicular length. Yeah, correct. Okay. So that's the calculating the magnetic field strength. In this case, it's found to be 0.654 Tesla. Quite a big unit. See, state two ways in which the current in the magnetic field can be reversed. Tell me two ways the current in the magnetic field can be reversed. How do you make the current to be upwards? So of course, either you change the direction of the current flow or change the direction of the magnetic field strength, right? And make the current flow from D to C, or make the magnetic field strength reverse the magnetic field strength. You get the force upwards. Okay, D, suggest way in which you can balance the rectangular frame when the force is reversed. Okay, now when the force reverses and the force is upwards, pointless you putting the weight here, right? You can't put the weight here. So you put the weight where?
On the side of the magnet.
Yeah, on the same side. You hang the same side. Same side. Yeah, reverse the side. Here you get the magnetic field strength. Okay. Good. So yeah, that's answer. Reverse the direction of the current, reverse the direction of the magnetic field. Remove sand from the tray and place weights along the CD. Okay, any part you don't understand here? This is current balance.
2.5. Oh,
Yep. Any questions?
wait. What's the value 2.5 there.
Which one? The 2.5 is the current.
Current.
2.5 ampere. Eh?
Wait, why do we
Okay.
need in that force?
Because we're using moment, right?
Yeah.
The magnetic force is the F, right?
Yes.
So the magnetic force formula is what? BIL.
Okay. I see.
Eh?
So what, that means the other side is the formula, and the other side is using moment.
Weight.
Yes.
H mg. Okay. So that's the technique. So that's the technique you have to use, lah. Eh? Okay. So that's your current balance. We are moving forward. Okay. Next, we're going to talk about is force on a moving charge. Okay. Force on a moving charge. Another subtopic. Eh? So you see this first diagram. The magnetic field will be exerted on a charged particle too. Eh? So you see the second diagram here, positive charge. The positive charge is moving to the left. Positive charge is moving to the left. Okay. Positive charge moving to the left. Magnetic field is upwards. B is upwards. Okay. Which direction the force experienced by the positive charge? This is a little tricky. Because if positive charge moving to the left, current will be where? To the left or to the right? Current also will be to the left, right? Current is what? Current is what? Rate of flow of charge. If the positive charge moving to the left means current also to the left. So if positive charge move to the left, make sure you point the middle finger to the left. And force is into the page. Check the direction of the magnetic field strength is upwards. Please use your Fleming left-hand rule. Do you get the force into the page? F, B, I. B upwards, current is to the left, so force is into the page, right? So you find the direction of the force. If you have a negative charge, second case, negative charge moving to the right. If negative charge moving to the right, this is the difficult one. If negative charge moving to the right, current you must point where? Current you must point to the left. This is the trap. Okay. The middle finger don't always shows the direction of the charge. It depends to the nature of the charge. If the charge is negative, then the direction of the current you must put opposite direction to the direction of the charge flow if it's a negative charge. So in this case, current is to the left, magnetic field upwards, still the force of the negative charge also going inward. We still use Fleming left-hand rule. So keyword, the negative charge, the direction of the force will be negative. If the negative charge moving to the left, then the charge will the force will be opposite. Okay. So a positive charge moving with a constant speed v at a right angle to the magnetic flux density. What will be the magnitude of the force? So how do you find the force formula? Now you get a new force formula for the charge. We get the force formula is, if we work out from F equals to BIL, you see, F equals to BIL for a current carrying conductor. A conductor as a length of L carries a current. What is the force? BIL. Here the I is rate of flow of charge, so put QOT. And L for a charged particle. If a charged particle move from here to here, the length we supposed to use is the speed of the charged particle times the time taken. So VT. So I is QOT, L is VT. So you get a new formula for force on a charged particle. It's BQV. Okay. If a charge, like for example, if a charge and magnetic field is perpendicular, the force acting on them is BQV. If the charge enters the magnetic field at an angle of theta, then it will be BQV sine theta. Okay, when do you use BQV sine theta? Okay, Why we use sine theta? Let's see. You have a magnetic field upwards. Sorry, you have a magnetic field this way, horizontal. Okay. If the electron moves like this, the angle is this angle. Okay. The force acting on the electric field strength is BQV sine theta. This is the formula to be used. So, can anyone can explain to me? The electron is moving like this. Okay, the magnetic field is to the right. The magnetic field, the electron, let's say, moving like this. Which direction the force will be? Up or down? Use Fleming left-hand rule. Get me the answer. So the electron is moving upwards, moving into the page. So the current will be this way, downwards. The magnetic field is this way. So where's the force will be? FBI. Up or down? FBI. So it should be upwards. Force will be upwards. So how much is the force? How to find this? BQV sine theta. How do you make this force bigger? You want to make this force upwards get bigger? Use a big magnetic field strength. Make sure the charge particle has acquired a big charge. And the very important thing, more faster the charge moves, more greater the force due to magnetic field. Okay, very important. This is one big difference between force due to magnetic field and electric field. Force due to electric field, independent of speed of the charge. Force due to magnetic field is dependent to the speed of charge. The charge moves faster, the magnetic force is greater. Okay, very important. BQE. And the fourth one is the theta. You want to get the greatest force, make sure the charge crosses the magnetic field strength at 90 degrees, like perpendicular. Then the force is maximum. When the angle gets smaller, the 90 degrees, right? The angle gets smaller, maybe 60 degrees. Is the direction of the force change? To the direction of the force change? Not magnitude. I'm asking, is it direction of the force change? The direction of force doesn't change. The angle gets smaller, the direction of force still upwards, but smaller magnitude.
Sir?
Yep. Yeah.
So that means that for a positive charge, for example, a proton moving, and for example, in this situation, right, if it's a positive charge and the magnetic field is going to the right, that means that it is going to the force is acting downwards. But if it's an electron, the force is acting upwards.
Yeah, correct.
Okay.
Okay. So but in the Fleming left-hand rule, the finger points FBI. The middle finger points the direction of the current. So if the electron moves to the upwards, means the current is downwards. So your Fleming left-hand rule must point downwards, your middle finger, to get the direction. That's the tricky part. Okay, so yes, so you see this diagram, the first one, so in the BB, this, angle between them gets smaller, the force direction never change, still upwards, but the magnitude drops. Okay. Okay, move on. So this is one example. A proton and electron enters a magnetic flux density 0.04 Tesla. Both particles travels with this speed. The charge is different sign. Draw on the diagram the direction of the magnetic force acting on the proton and electron. So here, down here, where's the direction of the force on proton? Use Fleming left-hand rule. Work out. Cross means the field is into the page. FBI. So for positive, where's the direction of the force? Should be diagonally like this, right? Upwards, but 90 degrees to the direction of the current. For the other one, negative move to the left, so current is to the right. Current should be to the right. Magnetic field is into the page. So use your Fleming left-hand rule, check. FBI, force still perpendicularly upwards, right? 90 degrees. Okay. So that's the direction. What is the magnitude of the force which magnetic force exerts on the proton and electron? So we use BQV sine theta. Sine theta in this case perpendicular, so sine 90, so 1. So yes, that's how it works. Any questions? Okay, no questions. Okay, let's move on. Okay. Deflection of charges. Okay. Before we do this, okay. You see this, the first picture. The electron is moving to the right. The force is downwards. The magnetic field is out of the page. Dot means out of the page. Sorry, the magnetic field is out of the page. Therefore, the force must be downwards by using Fleming left-hand rule. B out of the page. Current is where? To the right or to the left? Electron. So because electron move to the right, current is to the left. So your middle finger point to the left. Then you get the force downwards. Okay, now, question is, you can see the diagram. Electric field, parallel plate, electron going in, up positive, down negative. What type of path experienced by the electron? What shape the path it takes? Anyone? Goes up. What shape is this path? It's a parabolic path. Okay, it's a parabolic path. What is the condition to have a parabolic path? Anyone? What is the condition to have a parabolic path? The force must be acted. The force must be acted in one direction. The force always must act in one direction. The direction of force should not change. Then it takes a parabolic path. This is electric field. In magnetic field, when electron just now goes in, electron goes in. Okay, I take proton like easier. Proton goes in. Okay, magnetic field. Let's say into the page. Okay, B is into the page. Proton goes in. Go to the right. Where's your force? FBI. Up or down? B is into the page. Current is to the right. So force is upwards, 90 degrees. So at this moment, proton experience force upwards. So what happened to the proton? Proton mode, is it going to go straight? Make a turning a little like this. Because force upwards. So now the proton going to move this way. Magnetic field still into the page. Now the current is like this. What happened to the force? Is it still vertical or a little diagonal? It's going to be a little diagonal, right?
Yes.
Because force always perpendicular to the current. So what happened to the proton further? It will go up. So the force is always perpendicular. If force is always perpendicular to the direction of motion, what type of shape it takes? When force always perpendicular to the direction of motion, the type of path it takes is a circle. Take a circular path. Okay, so in magnetic field, the particle move in a circle or arc of a circle. Okay, it takes a arc of a circle. Depend if it's a radius is very big, you just take an arc of a circle, just a slight curve, but it's going to be an arc of a circle. Okay, or it make a complete one circular path if the radius is too small. But whatever it is, in magnetic field strength, in magnetic field, the charged particle make a circular path. In electric field strength, the charged particle makes a parabolic path. Another differences. In exam, they'll ask, why in magnetic field strength, the particle make a circular path? What's the answer? What's the answer? Why in magnetic field strength, the particle makes a circular path? The answer is, the force exerted on the particle is always perpendicular to the direction of motion. Okay, therefore it always makes a circular path. Okay, so go back to this PowerPoint. So you see the second diagram here. When the positive charge moving, the force is always acting towards the center, so it makes a circular path. Okay, the magnetic force act as the centripetal force of the charged particle, therefore results to a circular path. Okay, so because the charged particle move in a circular path, now the discussion get a little complex. Now you need to recall back all your circular motion knowledge here, because now they're going to ask you what is the radius of the circular path made by this charged particle. So you need to recall back your circular motion knowledge. What is your omega 2 pi over t, especially your centripetal force? What is centripetal force formula? mv squared over r and mr omega squared. Recall back. Okay. So from here you can work out your PDL. You can work out your PDL. In this case, the Fc is equals to the Fb, the magnetic force. Okay, charged particle. Hold on. Okay, so the direction we're going to make a turn. We always use Fleming left-hand rule to know the direction of the force. Then we can make sure which direction you're going to rotate. You see the first picture, the positive charge moving up. So current is up. Magnetic field is into the page. So force is to the left. Fleming left-hand rule. So we make a circle to the left. Okay. So the charged particle makes a circular path. The BQV should be equals to centripetal force, mv squared over r. B is what? The field strength. Q is what? The charge possessed by the charged particle. V is what? The speed of the charged particle moving. M is what? Mass of the charged particle. V speed again. And R is the radius. So we get a very unique formula, radius made by the charged particle. Okay. Where do we use this information? Where do you think this idea is very useful? Finding the radius of the charged particle can tell us about the property of the charged particle. Okay. You heard of cloud chamber? You heard of cloud chamber?
Yes.
Cloud chamber used in nuclear physics, right? You know, particle accelerator in the CERN, particle accelerator. The two particles go and collide. Then what happened? The two particles collide and it break into small substances. And the new particle which comes out, if it possesses charge, it produces a track. It gives a track. So in a cloud chamber, So the scientists want to investigate about how much of charge it possesses, how much mass is possessed. How they can do that? When the track forms, what they do? They apply what? They apply magnetic field into this region. When they apply a magnetic field into this region, then the charged particle will make a circular path. Okay, it will make a circular path. Okay, let's say you have two charged particles. You give a magnetic field into the page. One charged particle move like this. One. Another charged particle moved like this. Okay. Two. What you can tell about the charged particles? If you make a 2 round like this, okay, what you can tell about the charged particles? Which particle is positive? 1 or 2 positive? Anyone? The charge particles moving up, the charge particles moving up. This is the where the track happens. The track happens like this, then they split into two. Charge particle moving up. They apply a magnetic field here, only here. So it make the first particle makes a small circle. The second particle make a big circle. Okay, now the question is, the magnetic field strength is applied into the page. My question is, particle 1 or particle 2? What is the charge of the particle? One, what is the charge? How to know?
Yeah.
Yeah, one or two. One, what is the charge of the particle 1? Positive or negative?
Wait.
Yeah, positive or negative?
Wait, which direction is the magnetic field?
Magnetic field is into the page, cross.
Into the page.
Magnetic field is into the page. The charge particle moving up, then make a circle. Make a circle like in a anti-clockwise direction. Okay. So, what is the charge of the particle 1? So, how do you know? Anybody?
I think
positive or negative?
I think positive.
Positively charged. Why you say it positively charged?
Left-hand Fleming rule.
So you use left-hand Fleming rule. The magnetic field is into the page. The force is to this direction, into the circle definitely. So FBI. Put the force into the circle. B is into the page. So the FBI, the current found to be upwards. Current found to be upwards. So the current looks like same direction of the movement of the particle. If the current and the movement of the particle same direction, then the charge is positive or negative? Should be positive. Yes. So 1 is positive. 2 is negative. Okay, 2 is negative because the 2 is negative. 2 is negative, right? Yeah, the force is this way, right? The force is this way. So use Fleming left-hand rule again. Force is to the right. FBI, B into the page. Force is to the right. FB. Yeah. So the current is downwards. So it's a negative particle. So scientists can tell what is the nature of the charge of the particle by using a magnetic field. And another one thing, if both charge, then what else they can investigate? You can investigate about by using the radius, they can investigate about the what? About the mass and the charge possessed by the body. How they can investigate that? Just now, like BQV must be equals to MB squared over R. So the R is what? MB over BQ. So they know if the radius is small. So let's say they both come out with the same speed, and the magnetic field, of course, is definitely same. They can check about the mass per unit charge of that particle. Okay, if the radius is small, so what do we conclude about mass per unit charge of the particle? Smaller.
Mass is small.
We can't say mass is small. We say we say what? Mass per unit charge is small. Okay, because we don't know the mass, we don't know the charge. We pack them together. Radius small means mass per unit charge of the particle is small. Yes, that's what we conclude. So, what is the use of magnetic field? It's very useful in nuclear physics. Where we use it? In cloud chamber. What is the consequence of using the magnetic field? We can investigate about the mass, the charge, and the type of charge possessed by the particle. Okay. Any questions from here? Okay, go back. Okay, so yeah. So BQE equals ME square R, very important formula you need to remember. Then from here, we can find what is the period you're going to take and everything. The bottom question is fine. You don't need to remember. Remember the radius only. Okay. 1 minute for you. try to do this question. Figure out how you're going to do. F equals to BQV sine theta. Magnetic force equals to centripetal force. Yes. Okay, so you got the idea. So an electron of a charge is given, mass is given. It moves in a clockwise circular motion. It moves in a clockwise circular motion. Move in a clockwise circular motion. Perpendicular to the magnetic field of flux density of that. The magnetic force is given due to the magnetic field exerted on the electron. Draw a circular path of the electron. Indicate the direction of the magnetic field. So this is the electron. They say it is electron. It's a circular path, clockwise direction. Can you tell me the magnetic field is into the page, out of the page? Into the page, out of the page, make the electron to move in a circular path in a clockwise direction. Electron. Electron going down means current is where? Current is up. Force is where? Force is towards the center. So where's your magnetic field strength? Into the page, out of the page. FBI.
Out. Out.
Into the page, out of the page. FBI. F is to the left, right? Current is upwards, right? I'm using the right side. Current is upwards. So the magnetic field is into the page, right? Current is into the page. Yeah, sorry, the magnetic field into the page. Magnetic field is into the page, right?
Yes.
Yes, so it should be into the page now. So this is how the diagram should be. Okay. So this is how the diagram. The magnetic field must be into the page, cross. You can choose any direction. Force is down. Because electron move to the right, so current is to the left. Then you find the magnetic field is into the page. Okay, B, calculate the speed of the electron. So how do you find the speed of the electron? BQV. Do you know the speed of the electron? Force you know, V you know, charge you know. So you can find the V. Force is 5 times 10 power negative 14. B we know 8.2 times 10 power negative 2 Tesla. Charge of the electron is 1.6 times 10 power negative 19. Then you can find the B. Yeah, BQV. F equals to BQV. So find the V. Okay. So 3.8 times 10 to the power 6. Then calculate the radius of the circle. This is what we are discussing mainly, right? The magnetic force BQV equals to mv squared over r. So we can work out the radius. Mass, you know, mass of the electron, speed, you know, just now. Magnetic field strength given, charge given, so you can work out the radius. Okay. Okay, this is another question, but same way. I don't want to do this. You can figure it out. Okay. Okay, I want to ask another one question. One question is here. Okay, you have a magnetic field into the page. Electron proton, electron and proton moving to the right. Okay. Sorry. Top is proton. Down is electron. Okay. This is the region of magnetic field. This is the region of magnetic field. P. P is applied here. And the proton and electron enters that region. Both enters with the same speed. Trace the diagram. How's the path you're going to take? Which going to have a bigger radius? Which going to have a smaller radius? Which direction the circle you're going to make? Proton. Up is proton, down is electron. Electron, yeah. Both moving to the right. Both speed same. Trace for me.
Direction magnetic field.
Magnetic field is into the page. Cross.
Okay.
Magnetic field is into the page.
Photon will go down, electron go up.
Proton will go down.
Wait. No, wait. Oh no, proton go up, electron go down. Yes.
Proton will go up, electron will go down.
Yes.
Okay, now which will have a big radius? Proton or electron? Proton will go up, electron will go down. Which have a big radius?
Photon.
Investigate. Yeah, proton. Proton will have a big radius. Okay, it will have a big radius. Electron will have a small radius, maybe. Okay, so electron makes a small circle. Proton makes an arc of a circle because radius is quite big. So therefore, yeah, this is the pattern you have to draw. Because BQV equals to mv squared over r. So r should be what? R is mv over bq. So proton has a big mass. So big mass will have yield a big radius. V, B, Q all same. So big radius. So proton makes a big circle. Yes. Okay. So I go back to the electromagnet. So just now we done force on a moving charge particle. F equals to BQV sin theta. It makes a circular path because the force is always perpendicular to the direction of motion. So the particle makes a circular path. So we get the radius formula, very useful development because can use this information in nuclear physics to investigate about the property of the charged particle in terms of mass, charge, and the speed. Okay. And there is one question you can give a try. Okay. Same concept. Okay, so next I want to go through Hall voltage, but we take short break. I give you 10 minutes break, then we come back, we continue with Hall voltage. Okay, we just finish the Hall voltage. Yeah, then we can stop. We just do all voltage first. After all voltage, we talk about mass spectrometer and the current carrying. Yeah. Okay. So now the time is 11:57. So I see you back 12:05. Take 10 minutes break. Okay.